Good afternoon. I'm Glendel Calvo with my co-author, Ma'am Jasmine Malinao from the Division of Natural Sciences and Mathematics, University of the Philippines, Tacloban College, to present a research titled Mapping Hierarchies and Dependencies from Robustness Diagram with Loop and Time Controls to Class Diagram. The robustness diagram with loop and time controls, or RDLT, is used to model complex systems. There are no hierarchical abstractions and dependencies in RDLT. Since RDLT is relatively new, there are still limitations to its expressiveness. The RDLT is also lacking automation tools like verification tools, for example. To make up for this lack of software, we use equivalences between modeling diagrams like class diagrams or Petrinets with existing sets of automation tools. And these are the problem sets of our research. First, existing mapping of RDLT to CD is still incomplete. Two, no existing representation for hierarchical abstractions and dependencies in RDLT. Three, no mapping for such abstractions and dependencies from RDLTs to CDs. And the general objectives of our research is first to address the gaps in the existing literature in the RDLT to CD mapping. Second, represent hierarchical abstractions and dependencies in RDLT and establish their respective mappings from RDLT to CD. And third, to verify correctness of the mappings and illustrate the mapping of RDLT to CD with respect to the RDLT representation of the Schiller system. For the methodology, I will present the proposed mappings, which are divided into two parts: the static aspect and the dynamic aspect of RDLT components to CD. And this is the proposed mapping for the static aspect. The RDLT can be mapped to a package in class diagram or CD. According to the UML 2.5 reference manual published by Romba et al., a package is a grouping of related model elements such as classes, documents, or even other packages. And this is a name mapping. And the first vertex is the boundary object. It can be mapped into a class with a port in CD, meanwhile entity object can be mapped into a class without ports. And these are adapted from the mappings of U et al. Next is the controller, which is mapped into an operation of a class. And this mapping is released from U et al. And then the M attribute. The images in RDLT can be mapped into arcs coming from classes contained in a different package going into the RBS. In this RDLT figure, both of these arcs are in bridges or incoming arcs to the center of the RBS from the outside of X2. And the out bridges can be mapped into classes imported into the RBS in class diagram. For example, the SendD arc in CD imports can be used to connect the RDLT package to the RBS package or vice versa, despite the different hierarchy level. And this mapping of the center of the RBS, which is mapped in the private attribute of the class, is used from U et al. And then the RBS of an RDLT can be mapped into a package with constraint of containing only one class. Since RBS is the system, it can be represented as a package. And for connectivities, arcs XY, where owner of X is not equal to the owner of Y, can be mapped into a relationship between class X and Y in class diagram. And this mapping is adopted from U et al. Their mapping in class diagram was limited to association relationships only. Next is the type alikeness. In RDLT, the arcs are type alike if they are bridges of X or not bridges of X. In this example, Y1, X2, and Y2, X2 are type alike since they are in bridges of X2, while Y1 and X2 and X2 to Y4 are not type alike. In CD, they are type alike of class X if the arcs are are either arcs coming from classes contained in a different package going into the RBS or classes imported into the RBS, or the arcs are neither arcs coming from classes contained in a different package going into the RBS nor classes imported into the RBS. And the ownership is mapped into operations inside the scope of a class in class diagram. So all of these controllers are owned by X1, and in CD, the class X1 owns all the three operations. The input constraint is mapped into an attribute owned by a class in CD, and the parameter constraint is mapped into an attribute owned by class X2 and an operation parameter of class X1. So in CD, the parameter sendZ on operation Y3 expects the parameter Z in order to execute operation 3. And then the L attribute, which is the maximum number of times the arc can be traversed, is mapped into an attribute owned by a class in class diagram. And then we have the proposed mapping of the dynamic aspect of the RDLT components to CD. And all of these are new mappings since the previous literature did not take into account the time-dependent behavior of RDLT for their mapping. So the reset in RDLT can be mapped into a method reset in class diagrams. And then the reset updates on time for type-alike arcs can be mapped to a method reset T. To check if an arc is unconstrained or constrained is mapped the method check constraint in CD. To check if an arc can be traversed, the method check traversable, and to update the time of checks and traversals on an arc is mapped to a settings function set before the attribute in class diagram. And this is the mapping algorithm for building the package hierarchy in class diagram from RDLT. The recursive algorithm represents the package hierarchy setting, thereby supporting nested structures. And the second algorithm is the proposed mapping for RDLT to CD. And this part here is for the vertex set, the M attribute, the L attribute, C attribute, the C attribute again, and for the connectivities. The time and space complexity for the proposed mapping algorithms are quadratic, where n is the number of vertices. And this figure here is a representation of both generalization and specialization in RDLT. The vertices X1, Y1, and Z1 are the children or specializations of vertex W1. All of these children have access to the parent W1 and all its own controllers. Hence, the flow of the arc is from left to right. The C condition indicates that the children or specializations are based on generalization or the parent. On the second figure, the CD mapping of the RDLT representation is shown. The class W1 is the superclass and the classes X1, Y1, and Z1 are the subclasses. And then we have codependency. This figure shows an RDLT with export controller owned by vertex X1. In C, they're shown in this figure, the class X1 calls another operation, which is controller in Z2 owned by vertex V1 to export. And then this figure shows a trace dependency relationship between RDLT and class diagram. Both of these diagrams represent the same information. Then, as shown in this figure, the RDLT level 2 is a refinement of the RDLT level 1. This figure shows the CD counterpart of the refinement RDLT representation. Next, this figure is an example of substitution dependency in RDLT. The vertex X1 can be substituted by the vertex Y1. This figure shows the CD mapping of the represented substitution dependency. And then we have the derivation dependency, and this CD mapping is derived from this RDLT. And then the specifications of an absorption chiller in this figure is realized into an RDLT representation. While this figure shows a package element in CD to which the RDLT representation of the absorption chiller is mapped. And this is a sample RDLT model based on the portion of the RDLT representation of the chiller system. I use this portion for illustrating the RDLT to CD mapping. And this is a comparison of the RDLT to CD mapping of the previous literature and the proposed RDLT to CD mapping in this research. The noticeable difference is the use of package to define visibility boundaries for both RDLT and RBS, which is introduced in the study. The use of packages is functional in grouping together the related elements provided a more organized view on the mapping. And then a distinction between boundary and entity objects are mapped into classes was added with the boundary objects are mapped into classes with ports to indicate that those classes can interact with the environment. In the previous literature, boundary objects and entity objects are indistinguishable from each other. And then looking at the RBS in the figure of the previous literature, and the figure from this paper, it is more distinguishable in the latter than in the former. This improvement may not be so evident for smaller systems, but its impact is more pronounced when it comes to modeling complex systems such as the chiller system. Another difference is the outbridges. Since the proposed study makes use of packages, it is necessary to use import in order to include the class where the outbridge is moving in its namespace in order to connect. The use of the reset method can also be found in the proposed mapping. It indicates that the RDS class can reset its values upon exiting via the outbridges. The proposed mappings for the hierarchical abstractions and dependencies were verified to be consistent in terms of the representation. The identity to city mapping of the chiller system was also verified successfully, indicating that the mappings are indeed correct and applicable to real-world example. Representations of generalization and specialization hierarchies as well as several dependencies were formulated and mapped to CD, which was then demonstrated using the chiller system. And then for future works, further work needs to be done in representing aggregation and composition. The call sign, creation, instantiation, and access and bind dependencies also have to be added into the RDLT. Furthermore, algorithms for vertex deletion that enact the behavior of dependencies should also be developed. And then these are our references. That's all. Thank you.